there because they're LEDs, and you got LEDs or photodiodes or phototransistors, and those things require things to be put at a certain polarity. So when you look real close at it, when you look at the two leads, you should see one marked positive and one marked negative. I'm sorry, you see one marked positive and they don't mark the negative. They take for granted you know how to do that. So what we would do, depending on the voltage that we're going to apply these to, then that would determine how we connect the things. So what we do is we'll now I don't know if it uses a phototransistor or photodiode, but using just a photodiode, you'll be able to understand its operation anyway. So basically, it's like this. So you got to put a resistor in series with it, right? You understand that? Because if you put this thing across 5 volts, it's going to burn it up just like that. Because it's a photodiode, it only drops 2 volts. So you need to calculate a resistor. With the phototransistor, we put a resistor up here. Normally we put about a 1K resistor right there. And then what happens when some up here go ahead and breaks the beam, it turns this. Now think about this as a switch. So here's 0 volts. I close the switch. What would I get out? I'd get 0 volts out. If the switch is open, I would get my supply voltage, right? You understand? So it gives us the ability to use these things to sense blades, to sense what we call encoders. And this is what I have hooked up here. What did I do with it? If you got a printer, you probably got one of these on your printer. So when you turn your computer on, it goes over there and finds itself, right? You understand that? We have a special type of encoder. It's called an encoder. There it is with that. And this is called an incremental encoder. This is an encoder. I'll let him off with it. So notice these are nothing but a bunch of slots. And so we've got what we got here. The setup I've got here. So I've got I got my encoder, and then my encoder is positioned so it breaks the beam on my optical interrupter. And under the box, of course, this is where I have my resistors. So one of my resistors is down here, which you can't see. And then here's my other resistor right here. So what happens when I come over here, I've sized my resistors to power this off of a 5 volt supply. So the white tape, this is the output of my encoder, out of the output of my interrupter, and then this powers up. So that powers up my encoder, and then this is the power. Oh, what happened? Oh, I broke it off, guys. That's one thing about being in a wheelchair. You always jerk thinking things get tangled up in the wheelchair. So what I'm going to do is I'm going to put this on my motor. So as the thing spins, what's it do? It's breaking that light beam, right? And then we can come over here and look at the output of my encoder. Dang it. Been my scope probe though. So here, I got my scope hooked up here, and this is my oscilloscope. If I can get my camera hooked. So this is what the optical encoder is doing for me. So when I speed my motor up, the frequency is going to go up. I'll slow it down, it's going to go down. So how fast my motor goes? I've got it on 1 millisecond per division. How many slots are in there? So what we're doing is we're looking at one pulse. So this would be one of those little holes right here. This would be one. Right? So that's 1 millisecond per division. That's 1, 2, 3, 4, 5 milliseconds per pulse. But unfortunately, they're not in reduced speed. And what's the standard way of doing speed? How do we rate speed? In what? Rotational speed. So your car is in miles per hour. How do we measure rotational speed? Revolutions per minute. So how fast does the motor go? So what do y'all think the first thing I would do? Y'all geniuses. Come on. What would be the first thing I'd have to do? So 5 milliseconds per pulse. Then what I have to do is figure out how many pulses I get out of my encoder. How many pulses do we get out of this encoder per revolution? Anybody count them? Anybody got them? Or did y'all already bring it back up? Who's got the encoder? The little wheel I passed around. Charles, you got the encoder? The little wheel with all the holes in it?
Yeah.
How many holes are in there?
8.
Okay, so 8 holes. So it takes 5 milliseconds for one hole. Then I got 8 of them. So how many would it take for one revolution? How long would it take for one revolution? Yeah, one revolution is going to take, what did we say, 5 milliseconds. Multiply that by 8, it's going to be 40 milliseconds. So it makes one revolution in 40 milliseconds. Now I need to get that over to revolutions. So what I'm going to do, I'm going to take the reciprocal of that, and that's going to give me revolutions per second. 1 over 40 milliseconds. What would that give me? Huh? What's that? 25 revolutions per second. So how would I convert that into revolutions per minute? Times 60. So how fast is the motor running? So this is exactly what I would do in a PLC. I would just tell it to do the math, right? I could use this encoder. The more notches you have on the encoder, the more precise it is. So I just do this math in my PLC. In intro to PLCs, we don't have time to get into math, but if you take the advanced PLCs, we could do this very easy. I mean, all we'd have to do is just do what? Just I'd read one pulse, right? Or usually we read more than one. We read like 10 or 15. Then we'd convert it over. We'd take the reciprocal of it. We'll multiply it by 60, and then I could display that up there and get you the speed. So normally we put a lot more wheels so we don't have to make as many revolutions. So that means we don't have to count them as long, right? You understand? Does that make sense? So that's the way an encoder, so that's an optical interrupter. So what we do on an optical interrupter is the distance is fixed. And then we take something and we insert it in between. So, so let's go over there and look at this real quick on the line. I forgot about that.